Today I'm going to tell you what is Insar. Now imagine if I told you that a satellite orbiting hundreds of kilometers above Earth can detect the ground moving by just a few millimeters. Sounds impossible, right? Now this exactly is what Insar does. Insar basically stands for Interferometric Synthetic Aperture Radar. INSAR is a satellite based remote sensing technology that helps scientists monitor tiny changes on Earth's surface. These changes can be caused by earthquakes, volcanoes, landslides, or even the slow sinking of cities. The amazing part is that it does all of this without touching the ground. It simply uses radar signals sent from the space. Now, let's look at the INSAR workflow step by step. First, a satellite flies over an area and captures a radar image. This is our first image. Then, after a few days or even weeks, the satellite flies over the same area again and captures a second image. If the ground has moved between these two visits, for example, because of an earthquake, the radar waves travel a slightly different distance. Then, by comparing the radar information from these two images, scientists can measure exactly how much the ground has moved. Basically, this process is actually called as phase difference. Then, the last step after comparing the phase difference, we kind of generate interferograms. Now, uh, this is an image basically. The pass one is basically the pre-movement, like the first session of monitoring that was done, and pass two, the post movement, is basically the second round of monitoring which was done, where a certain phase difference was occurred. As you can see here, the radar part depicted in red is actually showing how much deformation has actually taken place. Now, let's understand the most important concept of INSA. It's basically the phase. Now, think of radar waves like ripples in water. The satellite sends these waves to the earth and they bounce back. If the ground hasn't moved, the waves return almost exactly the same. But if the ground shifts even slightly, the waves travel a different distance before returning. This tiny difference is called the phase difference. When scientists compare the phase from the two images, they kind of create an interferogram. As you can see in this image, the first time when the satellite monitored, it actually generated a phase difference. The second time also when it did the monitoring, it generated a phase difference of the same. Then by comparing these both phase differences, they kind of generate an interferogram. Now, the colorful rings which you can see are called as fringes. Each fringe represents a certain amount of ground movement. So, by counting these fringes, the scientists can estimate how much the earth has moved. Now, talking about the wrapped and the unwrapped phase. Now, as you can see, the interferogram initially shows repeating color patterns. Now, this is basically a wrapped phase. In this figure B is basically the wrapped phase, which kind of shows a lot of repeating color patterns. And figure A is basically the unwrapped phase. Now, these repeating color patterns in figure B kind of make it difficult to know the total amount of ground movement. So, therefore, to solve this problem, scientists actually perform a process called phase unwrapping. Now, in phase unwrapping, it's very simple. It's just like removing the repeating pattern and converting it into a continuous map showing the actual ground displacement that has taken place. In very simple words, wrapped phase shows the pattern while the unwrapped phase tells us the real movement. Now, let's move on to the challenges that are faced while INSAR measurements. Now, although INSAR is very accurate, it also has some challenges. One of the important challenge is decorrelation. Now, if ground changes too much between the two satellite images, for example, due to vegetation growth or water, snow, landslides, the radar signals no longer match properly. This creates noisy areas where measurements become unreliable. Other factors such as atmospheric delay, even satellite orbit differences, and even uneven terrain can also introduce errors. uh, Talking about orbit and topography, it is basically the difference in satellite orbit between passes, and complex terrain can actually introduce phase errors that must be uh, carefully corrected during processing. That's why scientists carefully process the data before drawing conclusions. Now, moving on towards another new concept, which is line of sight. The satellite can only measure movement along the direction in which its radar beam travels. Say, suppose, take an example. If the ground moves towards or away from the satellite, INSARs detect it very well. But however, if the ground moves sideways, as you can see in this second figure, the ground has actually moved sideways. Uh, then the satellite cannot measure the movement accurately. As you can see, the red part in the radar wave is actually showing that due to ground movement or due to uh, sliding of ground, it's not kind of able to measure that movement accurately. Now, to get more complete picture of ground deformation, scientists actually combine images taken from different satellite viewing directions. And the viewing directions could be either in ascending order or in descending order. It's basically, it actually gives an approach from different angles, and it helps to reconstruct a more complete picture of 3D ground motion. Now let's have a look at the applications of INSAR. Now INSAR actually has a lot of uh, real world applications. I have just enlisted a few ones here, which is basically earthquake monitoring, volcano deformation, landslide detection, land subsidence, infrastructure monitoring, and fault movement analysis. Then, uh, moving on towards the key takeaways. Uh, First one is phase difference, phase comparison basically. In this, INSAR compares the phase of two SAR images to detect ground movement. So this basically is the phase difference. As you can see, this is the phase 1 and this is the phase 2. Due to this deformation part here, which is denoted in red, this is the phase difference caused due to sliding of land or land deformation. Then, moving on towards the next key takeaway point, millimeter precision. It measures deformation with millimeter to centimeter accuracy from space. Moving on towards next, interferograms and fringes. Colorful fringes, visual displacement, and wrapped phase must be unwrapped for real measurements. Next is known limitations. Decorrelation, atmospheric delay, and line of sight geometry affects measurements. And talking about the wide applications, it's basically used for earthquakes, volcanoes, landslides, subsidence, and infrastructure monitoring. Thank you for your attention, and I hope that this presentation gave you a clear understanding about what INSAR is and what is the process included in INSAR. Thank you.